bigger the better. Eugene, seriously, what's wrong with you today? Yeah, I won't post the wrong address until Jenna told me today. Like, it's the wrong. I mean, she did not know it's the wrong address, but she told me I checked it's the wrong address. Right. So this is the distribution for the shear. Now this is due to torque. Right. This is due to shear force. Right. This is a combination of axial and bending moment. Right. So this is the distribution now. And you realize that at the centroid, right, the shear stress is equal to 0 for the torque down here. You guys say, oh no, right? Okay. Right. So we are going to combine everything in our analysis now. Okay. So the first, so given a problem like this, right? Simple problem. Okay. Right? It's simple. You have an axial load, you have a bending moment, you have a torque, but you have to understand how the distribution proceed. And some of you who are working in engineering companies, okay, I'll tell you this, okay, a lot of them just use software. It can be finite element, or it can be a software that specializes in shaft calculation that integrate everything for you. Okay, I'll tell you. I'll be real honest with you. Okay, and they also have if different criteria. What is the different size of the diameter? Okay, true enough. Okay, you guys got me there. But what if now those software has very unique solution in the sense of based on the loading condition. Okay. If your condition of loading is not the same as what the software has, you're done. That's what I'm teaching you. What if the software does not have the loading condition that your company or that the situation is loading is not there? What will you do? Okay, you cannot call the company and say, hey, could you deliver this for me? Yeah, they will if you have money, lots of money. Okay, I don't want that to happen to you guys. It happened to me before when I was working with Rolls-Royce. I don't want that to happen for you guys. Okay, I want you to be able to analyze what's going on and know the calculation. That's the value of an engineer. Okay, not rely on artificial intelligence. Okay, I believe you guys have real intelligence, right? So we have to, before we go there, we have to, the first thing we have to do is, okay, the first thing we have to do is investigate or analyze which location has the highest stress state. Okay. So you have to know, right, at what stage or at what location the structure is under the highest stress. This is critical. Okay. So I'm going to copy this. You need the diagram. So to be frank, where we don't know yet. Okay, we don't know yet. So what do I mean by where? Okay. So again, based on transformation. Now, transformation is ever so important. Okay. 3D analysis, you mess up your transformation, you're game over. Okay. So I'm going to draw out elements. So this is where you hear, last week we talked about elements. So this is where, so we are going to position, this is my element A. Over here is my element B. Over here is my element C, right? A, B, C, and over here is my element D. Right? Some of you will tell me, Eugene, why are you picking them 90 degrees apart? Okay. The fact it's 90 degrees apart is because of this condition over here, the distribution. Okay. The distribution is either at the 0 or 180, you have the highest normal stress, or sorry, 0 and 180, or at 90 and 270 you have maximum shear, or the torque is constant all around. Okay, the torque is constant all around. Okay, so that's why I picked them at 90 degrees relative to the transformation. Okay, relative to this transformation.
Eugene, I have a question, please.
Yes.
For the transformation, I know Y is going up, but can X and Z be interchanged, or is that?
You have to oblige to right hand rule. Hello.
Yeah, I'm here.
Yeah. So if you want to change y and x and z either way, your y has to be pointing downwards.
Ah,
Okay. So right hand rule is critical. Okay. Right hand rule is not just critical for electrical engineers, also critical to us. Okay.
thank you.
So let's look at the elements now. Okay. Let's look at elements. Okay. So we have element A, B, C, D. So what we're trying to do down here, okay, I will recall to you guys, okay, is we are going to locate the highest stress state. Okay, where is the highest stress state? I mean, if you don't know, okay, you will do for every element. Okay, you do for every element. Then you will tell me final exam not enough time, right? No, okay. In real world, you also, yeah, you could do every element, okay, but not for this case, okay. Right. So then you have, right. So we are going to look at the first stress state, which is equal to our torque. Is our shear stress due to TR over J. Right. So based on the distribution, we know that as long the radius is the biggest, okay, which all point A or element A, B, C, and D has, right? The shear stress induced by torque is the same. Okay. So all of them CTR over J. Okay. All of them fuse the TR over J. Okay. All of them fuse the TR over J. Now for this problem, there is no shearing force, but I'm going to put it in. Okay, I'm going to put it in. Right, you don't see any shear force or shearing stress at all, right? Shear force. So I'm still going to put it in case you guys later on will design and requires a shear force. All right. So this shear force is not there. I'm just giving an example. So now, if we have a shear force V acting down here, okay, we have a shear force V acting down there, right? So for point A, right, your shear stress will be equal to 0. For point B, right, it's going to be, or element B is going to VQ over IT. For point C, 0. For point D, VQ over IT. Okay. So now, if I were to ask you based on shear, right, based on shear, which element will you choose? Anyone? It's just based on shear. Which element will you choose?
B or D?
Yeah, B or D, right? Okay, but it all depends on the torque. I'm not going there yet. Okay, or direction of the torque, because the shear force, everything goes to the same direction. So the next one, we have our P over A, right? We have our P over A, right? So normal stress is due to P over A. Okay, so P over A, everything is the same. All of them are minus, because all of them are going through what? Compression. And the final column, right? So next one is due to bending moment, where normal stress is equal to M y over I. Okay. Now, this case, you have to be very, very careful. Why do I mean that you have to be very, very careful? Because now you have to know what is tensile compression. So the 1,500 pound-feet is acting this way. This will be compression. This will be tensile. Now you see why I teach you the moment arrow, right? I don't need to think. I just need to remember head of the moment arrow is compression, the tail end is tensile. That's it. Okay, you don't need to mess around. Is this positive or negative, right? Okay, so just to help you, and you guys are really good on that because STEM test 2, you guys did so well, which I'm so proud of you. Okay, so point A is going to be tensile. My over I, positive. Point B is going to be 0 because it's at the centroid. Point C is equal to minus my over I. Right? And point D is equal to what? 0. Okay. So I'm going to draw a line down. So question for you. Which element will you calculate? So let me go further, okay? So the shear due to torque, this has been normalized. Normalized means what? Everyone sees it, does not matter. Okay? Everyone, A, B, C, and D, the shear stress induced by torque is the same. It's all the same. Does not matter. Does not more the same. Okay? We don't have any shear force. Okay? Now, which element will you investigate? Anyone?
C.
Why C and not A?
Because both normal stresses are compressive, so
Well
it'll be higher.
Okay. So we are going to investigate point C. Okay, element C. You have to go into this sort of detail. Why is that? Because when something goes wrong and is designed by you, okay, someone like me as a principal engineer represents the Queen's Court has to know what you are doing. Okay, a lot of times companies got heavy fine in court is because their documentation of analysis is very weak. Okay, and I don't want that to happen. Okay, if I'm going to review a case in the future and you guys are chief engineers, I expect this level of analysis. Okay, not just we assume, and then when something goes wrong, like for civil engineers, something goes wrong, a lot of people will get injured. Okay, so we don't go there. Okay, so this is the level of analysis that we go for. So when someone like myself or another engineer look at it and they say, okay, this is proper engineering work. Okay, this is what you guys are paid for. Okay, right. So we are going to now we hone in already. Okay, now we hone in already. Okay, so we are going to investigate element C. We're going to investigate element C.
Can you just quickly explain why again?
This is because, okay, TR over J is for all the elements, right? There is no shearing stress. So we put point C is because both of these are negative and will generate the highest magnitude. Whereas element A, one is negative, one is what? Positive. It will not generate the highest magnitude, okay? That is the only reason, no more and no less, okay? Right. So from here, we are going to investigate element C. Okay, we're going. So I'm going to draw now. When you visualize an element, okay, you have to make sure there is no obstruction. Okay, so what do I mean by that? So we are going to look at element C, right? We're going to look at, excuse me, we're going to look at element C. The only way to look at element C is you position your eyes down here. Right? That is your eyebrow. Sorry. Or eyelid. Okay. So this is your eye. So you have to go under the what? Under the shaft, right? To look at element C. Okay. So when you go under the shaft to look at element C, this is what you get. Okay. So if I